All right, this is the first lecture where we're really going to show the power of the Mach principle, but also all of that projection operator analysis in order to produce, and virtually with no effort at all, the wave functions for quantum rotors. And that's nuclear, molecular, or even atomic. Quantum mechanics can really benefit by looking at things this way. We'll first review the algebra that lets us do this, and that's the harmonic oscillator in 2 dimensions, basically getting the U2 representations of Hamiltonians, and then allowing you to take it to the quantum mechanical limit where we can raise and lower the quantum numbers of the oscillators. And in the process, take care of a very annoying part of quantum theory of angular momentum, which is the raising and lowering of spin operators or angular momentum operators. So that's something I want to just review a little bit of what leads up to that first, and then we'll see how the angular momentum algebra in general, the Lie algebra, comes very naturally from the Lie algebra that's already contained in the unitary 2 group. Then we'll get some interesting geometry just by using the quantum eigenfunctions that we get for U2 and R3 wave functions. We find a what we call angular momentum uncertainty cone and angle. And one of the things that's not discussed very often is how the angular momentum theory in 3 dimensions has a very unusual uncertainty relation, which is very powerful, can be used quantitatively. And then it makes you think that we could go back and do the same with things that happen in the oscillator side of the story. So anyway, we're going to be actually producing all of the representations of both these groups quite easily. It's basically a high school algebra from here on. Okay, so let's get started. The thing I should point out is that these single click website things are available, and I'll be listing the ones that are appropriate for the web apps that actually produce the wave functions that we're going to be showing. So it will be very easy for you to reproduce some of the features that we'll be talking about in this lecture. Okay, so the review, if you recall what we were doing last time, was we were writing the A, B, C, D Hamiltonian of a 2-dimensional harmonic oscillator in terms of the number operator 1, 1, that's the 1, 1 component of the classical, semi-classical Hamiltonian. Then there's a 0-point energy associated with it. Then there's the 2, 2, that's the other diagonal component of the asymmetric diagonal members of the Pauli algebra that gives rise to this semi-classical Hamiltonian we talked about in lectures 6 through 7 or 8. And then the off-diagonal components, there is a real and imaginary part of that. The B standing for bilateral symmetry. That's the Pauli operator X that is symmetric on the anti-diagonal. And then the complex part of this, the one that has the chirality generator for our oscillator and polarization analysis. Both of these belong to the 1, 2 component and the 2, 1 component of our original A, B, C, D Hamiltonian. Well, now they're sitting on top of creation operators, creation destruction operator products that will let us make this matrix here that goes forever. This is an infinite dimensional matrix corresponding to all of the possible pairs of quantum numbers for a 2-dimensional oscillation. And just to show you a couple of the matrix elements, they're all generated by the A dagger, Eigenvalues, but also Eigenvalue off-diagonal elements. For example, the one that's being used right here to get that square root of 2 that sits in front of the 1, 2 operator's product in this, for this quantum number 0, 2 to be transformed over to the angular momentum state 1, 1. So what we'd be doing then was we'd be using this operator, A dagger 1, A2. That means the A2 destroys something for the second dimension. It destroys one quantum of the second dimension. This will hit that and make that with a matrix element that is a square root of the largest of the two numbers, which is the n2 that we started with. This is n2 minus 1. And then along comes the creation operator for the first dimension. That's this quantum number right here and here. It takes this number right here and raises it by 1. And then the larger number is that, so you have a square root of n1 plus 1 for that. So the square root, if we're starting with n1 in this particular case equal to 0 and n2 equal to 2, all right, you're going to get the square root of 0 plus 1 and the square root of 2 right there. The 2 is the one you remember was brought down, so we use it directly. And then we'll get what we had before. This was 0 before. We add 1 and we subtract 1 from that by using the A dagger A operator. Okay. So here's the formula, there's the result, and that's all there is to it. And it goes with this particular component, which is B minus IC. So you see, even the off-diagonal elements for all of the matrices that you could possibly think of, up to very high angular momentum. And by the way, that's another thing that's really powerful about what we're doing here, is that angular momentum of 20 or 50 or 200 or even 1,000,000 doesn't bother us. We can work with it. And that's very good because there are some nuclei and molecules that are doing very strange things at very high quanta. So we're in the ones and twosies right here, but we're going for much more. So in any case, this was the start of our discussion using the little Indian lexicography of the ordering, but we need to reorder this. That's really the only tricky part of this, is to reorder this to bring this matrix into a nice block diagonal form. So we could go way ahead and just attack a single block very quickly. So when we do that, what we're going to be doing is asking if I can collect all these states up here, 0, 0, 0, 1, 0, 2, 3, 4, 5, then 1, 0, 1, 1, 1, 2, 3, 4, 5, and 2, 0, 2, 1, 2, 3, 4, 5. There's an infinite number of states in each one of these blocks. I want to take only those that have the same total quantum number and define each block by that total. So the boson number n1 for the first dimension and n2 for the second dimension, they're going to sum up to give this new quantum number. That's a very important quantum number for working with oscillators. And then it's the difference between n1 and n2 that describes the states that are going to be within each of these blocks that we're making in this slide. So we've seen this before, but anyway, we bring the things together by taking this one and putting it in a block by itself. That's called the vacuum. And then the next stop right here is this block right here, and that's just a repeat. It is transposed because we're using the little endian indexing. If we use the other, we can get that straightened around. We have D up here instead of down here, and D should be switched to correspond to our original ordering. But in any case, I'm putting here the two states, 0, 1, and 1, 0. That's a one quantum states. The two of them are possible in this two-dimensional oscillator. Then the next stop is, if I'm allowed to have the sum of them be equal to 2, there are three ways to do that. 0, 2, and 2, 0. But then there's another possibility, and that's the 1, 1. So that makes up a 3 by 3 matrix, and we just worked out one of the components of it. The one that goes with B minus IC is sitting there. There's another one just like it for the next one that happens. And these are basically, if you write all of the B's and C's equal to, B and C equal to each other, or take out the, make C 0, make it bilaterally symmetric. This is a Hermitian matrix. And so will the next one be, and so on. So that's the basic idea of the oscillator giving us what's going to be the quantum theory of angular momentum as well. And we knew that something like this had to be because of the homomorphism between the rotation in our the space we live in, the three-dimensional space. We knew that there was this connection to the complex space in 2 dimensions, the ABCD parameter space, you might say. So we knew this was possible from just a topology of the three-dimensional space and its connection to complex 2-dimensional space. All right, now if you're talking about eigenvalues, and that's what we often do, we say, I just want to do the asymmetric diagonal and just have number operators, then these are my eigenvalues. If that's the case, I don't have to do any further work at all. But this form that they take is the form they will take in any eigenbase, not just the AD basis, but in the B basis, in the C basis, in any combination of A, B, C, and D. They're all going to look the same as far as the algebra goes. So that's kind of interesting. And there we will discover that the numbers that are important are, again, the sum of the quanta, but this time divided by 2. That's called the J, total angular momentum, in the R3 world. And then N1 minus N2, but also divided by 2. That's called the azimuthal quantum number, M, or magnetic quantum number, in the R3 world. So we can go ahead and just assign these things angular momentum levels as well as the oscillator designations. And remember, of course, that the total quantum number for the oscillator is 2 times the quantum number that of the angular momentum in the R3 world. This is another one of the 2s and 1/2s that is part of the connection between the 3 by 3 world and the spinor world of the 2 by 2 world. So this then sets us up for what we talked about before. There was an average energy, a overall phase was determining and determined by this, and then there was the beat frequency omega in the the R3 world, which was the difference between +1/2 and -1/2 in the U2 world. So this is all coming to bear here to make this is the general formula that will be true no matter what type of quantum numbers you're interested in. We're now imagining we're interested in the Z quantum number or the AD quantum numbers. Here spin up and spin down, or could be A and -A, Z and -Z quantum numbers. Okay, here's the sum, there's the difference, there's a 1/2 sitting there to make it so I can write it in terms of this frequency here, the beat frequency. So this is probably a simpler way to state that. Okay, so this is a good part of the review. And when you look at these things, you see that besides the vacuum, which is very trivial, this is the one that starts it. This is the fundamental. If we're talking about a molecule's vibration that has 2 dimensions, such as CO2 or the E vibration of SF6 or anything like that, then this will be the fundamental level. This will be the vacuum level, and transitions between this would be called infrared spectroscopy. But this is going to go forever. You can go as high as you want with these quantum numbers, but you do it in steps: even, odd, then even again, then odd, then even. And I mean even in some permutational symmetry of these wave functions in terms of reflection symmetry of them, but also in just the numbers. This is an even number right here of half quanta, you see. This right here, this is one, if you're thinking of these things as integral quanta, which we do when we do the ABCD model. Okay, so this will be odd. Then this is even again, this is odd, this is even, you see. And that is connected in some way, we're not completely clear on this, but connected in some way with the Pauli versus Bose statistics or parity symmetry. So the things I'm doing in green here are very boson or Einstein-Bose-like. The others are the Pauli-Fermi antisymmetric combinations. And the wave functions that you make in the oscillator world are indeed odd and even for the green, odd for the red. So there is that to think about as well. Then there's some interesting stuff that have to do with the intersection, but we're not going to get into that. That's another kind of symmetry that this has. So that's the end of the review. Now we're just going to do something that we started to do in the last lecture, and that was just look at the 2x2s, as we've already done back in lecture 6, 7, 8, 9, and so forth. We had the discussion of spin operators versus angular momentum, or Pauli operators, sigma operators versus spin operators. The spin operators, you recall, were the Pauli operators with an extra 1/2 factor attached to them. And the big omegas, not the little lowercase omegas, but the big omegas were 2b for this one. A plus d over 2 went with a minus d, and the 1/2 went into the operator, not into the actual coefficient. So these three numbers here were the three components of the uppercase omega, the horseshoe omega, the one that goes with R3. So that's what we're really setting up here, is a situation that makes sense to do in the R3 space, where the frequencies of things that happen is twice as fast as what's going on in that base space of just two spin-a-halves, you see. They only have half a spin. This has got the whole spin, okay? And the operators we're going to make out of these, or have made already, x, y, and z here, this being B, C, and A by that old notation, okay, B, C, and A. Well, that's the new notation. I said the old notation is this. This is Pauli's, Jordan's original notation. Okay, but you see the idea is a Hamiltonian is a linear combination of group operators here. So we're going to take individually these group operators and get their representations too. So we're kind of going backwards a little bit from the way we've been doing it, but still the idea that you make pieces of the Hamiltonian. This is the fundamental Hamiltonian, but now we're going to start raising the quantum number, you see, for the vibration from 1 to 2. That means we're going to go from j equal 1/2 up to j equal 1. Well, that's the 3x3 block that we were just getting the square root of 2 coefficient for b minus ic. This is now turned around, so the a starts the thing off, a plus d, and d ends it. There are the 4 coefficients really, but 3 active coefficients, the one that describe angular momentum, are now sitting in front of, and these are 3x3 representations of these x, y, and z spin operators. And the Z is the one you can recognize immediately because instead of just being spin up and spin down, it's spin up, 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 down, and down, down. Down, down comes out to be -1 because you're summing 2 minus a halves. Okay? So, this is all very familiar. This is the vector representation of the group U2 or R3, either one. But it's a representation just of the generators of the group, not the operations yet. We still have to get that. That's going to be the middle of this lecture, how you put these all together to get the Euler representations for any angular momentum. Next stop is nu equals 3, or j equals 3/2. That's a 4x4 block. I now have 4 quanta. I can put it all in the first dimension. That's 4, 0, and then I can make it a 3, 1, and then a 1, 3, and finally 4, 0, 4. Those are the possibilities when you're thinking of the quanta. Okay, and now when you apply the operator, you start seeing square roots of something larger than 2. 1 or 2 is what you saw when you compare what we've had so far. But there is the representation of the Hamiltonian, and there are its generator parts, including the unit operator. Okay, so this is really a 4-dimensional algebra.
Sorry, can we name these 4x4 or 3x3 U2 or R3?
Well,
their block is, yeah?
They belong.
They belong.
Yeah, each block is part of the giant matrix we started with, which goes forever. But we reorganize it so that we only have the collected states in each block to correspond to a total of the n1 plus n2. So here, n1 plus n2 is 1. And there are 2 ways to do that, 1, 0, and 0, 1.
Do they belong to U2?
Well, these are generators for both U2, which is sort of an enveloping, or what they call a covering group of the space we're working with, including the space we live in. But you remember, the space we live in is covered twice. Remember how you had to go twice around in order to bring the spin phase back?
I'm wondering why we have 3x3 or 4x4, and we think that they are included in U2. They are not included in U2.
Oh,
they belong to a bigger space. Each part of.
Let me answer that by taking advantage of a little bit of the group theory, which we already know. If we were talking about the group C3V, right, it was really a 2-dimensional situation, a triangle in 2 dimensions. But if you think of the actual motions, it was 6-dimensional, right? Because each one of them could do 2 dimensions, right? If you're thinking about vibrations, right? So it's the order of the group was 6. But a 6x6 matrix would be reducible, no matter if you came with me, that representation. Yeah. It would be reducible to 1 by 1, A1. Another one, 1 by 1, A2. Okay? Now that's already more complicated than what we've got here, because there's only one scalar representation, only one by 1 representation for this group. But there is also one 2 by 2. Okay? And that we share with the group C3V. Okay, it had a 2 by 2 called E, right?
Yes.
Okay, so that accounted for the whole group. Some of the squares of those dimensions came out to be 6, right? Okay, so now the best question to ask is, how many elements are in this group we're talking about here, right? I mean, you go on to the octahedral group, it was 24, right? And there you had 2 1 by 1s, A1 and A2. Then you had an E. Then you had 2 3 by 3s, right? You sum those squares up and it comes out to 24, which is the order of the group, right? Now all these things that we proved for that are true for this, but they're not terribly useful because the number of elements in either O3, R3, or SU2 or U2, all of those groups are slightly different. And the first class, the R3 and the O3, is kind of half-assed compared to the U2. The U2 covers the whole thing, so it has 2 times infinity elements if the R3 has 1 times infinity, okay? But it's still infinite. So that means that we're going to have an infinite dimensional representations that are irreducible for this group. And that's what we're finding here. So this goes on forever. The next stop is 5 by 5, which is very important. That's angular momentum 2. That's the tensor representation. Very useful for our 3-dimensional space work because we can put tension on it. That's the Einstein Tensor, right? Okay, and then it keeps getting bigger and bigger and bigger until, wow, we've got to take advantage of the power here to see what those are. So each of these is just a bigger irreducible representation of a group that has an infinite number of elements. That's a lot to swallow at this point because we haven't really talked about infinite groups. We've got one here, and so we're taking it on. It is the most famous of the infinite groups, obviously, because we live in a space that's governed by it. Does that help with the answer on this? Okay. So I'm just going to stop right here, but in a minute we're going to look at the 5 by 5s. I'm not going to do too much with the 4 by 4s. I'll look a little bit at this, and I'll look at the 5 by 5s because they're the ones that you're really familiar with if you start any quantum course that does SPD orbitals. So we're going to look at the P and the D. S, I didn't even bother to write it here, is nu equals 0. Okay, and J equals 0. Okay, so what we're going to do is, in general, if you have an angular momentum J, or a principal vibration quantum number of 2J, you're going to have 2J plus 1 states. J equals 3 halves, okay? 2 times that's 3 plus 1 is 4. This one right here, J equals 1. 2 times that plus 1 is 3. So that's just doing a quick accounting of all of the ways to put the boson quantum numbers that I can think of when I have 2 possibilities to place a sum that comes out to be this thing. 2J is N1 plus N2. So this number is very important. That's the dimension, that's L of the irreducible representation, you say. So we've got the first of the characters of this infinite group are coming here, you see. The dimension obviously is the first character that you want to know about. So in any case, we're going to have a frequency omega x associated with this, omega b, omega y, omega z, you see. And then we're going to have some big matrix that's 2J plus 1, the J block. You see, somewhere, down there, we're going to talk about angular momentum 20, so way down there is something that's 20 times 2, which is 40 plus 1, 41 by 41 matrix that we're going to be writing formulas for and also visualizing. That's what we're after. Okay, what we'd like to do, just to make it so that you can see the connection between this boson way of looking at things and the usual raising operators and lowering operators, namely these things, we're going to make sense out of those. But right now, one of the things you can see is that I can rewrite this Hamiltonian in terms of an Sx plus Isy, a phasor operator you might call it. And there's its conjugate, Sx minus Isy. And all I have to do is make a phasor variable out of the frequencies, the big frequencies in this case. So I have an x minus I omega y multiplying sx plus I sy. That will give me part of this thing, and then I have to do it again to make it thing. This is just going back on the factoring of the harmonic oscillator that we turned x squared plus p squared into x plus ip and x minus ip. Here we're doing it with each component. And then we're going to leave this alone. Okay, so this thing right here divided by 2 comes out to be this right here, a linear combination of spin operators, these three operators, but a representation of them that's enormous, possibly 41 dimensions for angular momentum 20. Okay, so let's look at those operators in detail. The raising and lowering operators, which are just sort of pulled out of thin air in any treatment of angular momentum, and I'm doing sort of that right here, but I'm trying to make a connection with the creation and destruction operators, and that connection is right here. It's really very simple. We kind of saw this already when we know if there's an operator that raises one whole quantum of angular momentum, then the way the A daggers and A are going to have to do it is halvesies. I'm going to have to, in order to lower the angular momentum by 1 or raise it by 1, if I'm going to raise it by 1, I have to destroy a spin down that raises me by a half, and then I create another positive spin a half. That half plus a half now gives me I'm up 1. So this is an S plus 1 operator, whereas these each are plus or minus 1/2, you see. Here's the lower, it's going to destroy a spin up, brings me down by a half, and then I'm going to create another minus a half by creating a spin down. Okay, so we saw that already. Okay, this is part of our creation destruction algebra. But I want to show you that it is the same as the operators that these people, pull out for angular momentum, without mentioning that the bosons are behind the scenes. So when I do that breakup of this, say it's S plus here, x plus iy, this is what it looks like. You see, it's Sx, which is a half, and then it's I times Sy. There's your old Pauli spinner with a half. This is Pauli spinner X, this is Pauli spinner Y. Okay? Well, add those up, all right? See what you get. Okay? You get a half here, and then you get an I times minus I. That's another half. That gives you a 1. Here it cancels. You just get our elementary projector. This guy. That's a representation of this guy. And then its flip is the representation of this guy. So you see, it's really showing us that the elementary projection operator, P1, 2, is what we're getting here with regard to, well, this is a general, we're very much interested in getting irreducible projectors. Here they are. They're this, you say. Okay? So it makes a lot of sense. Now, the Z part, that's what we've always had. And so there you are. That's all there is to angular momentum raising and lowering operators. But we'll carry it through here. I want to go ahead and make sure that we cover everything that you would cover if you were doing this the old-fashioned way. So we're going to make use of S plus, S minus, and SZ. Now remember that SZ is the N1 minus N2, number operator 1 minus the number operator 2 eigenvalues, right? So that's the eigenvalues of SZ. Number of spin ups minus the number of spin downs times a half, okay? That's going to be our angular momentum, right? So here, once again, we say I create a spin up, okay, using a creation operator on the vacuum. Should really be writing 0, 0 here, but we'll just do shorthand here. So there would be the spin 1/2, was z component plus 1/2. There'd be this component total 1/2, and then the z component minus 1/2. That's the way you write angular momentum states. I warned you about this too. We put the label of the irreducible representation up here, and then whatever subgroup, in this case the z rotations, has its quantum numbers, we list them next. So this is a very simple subgroup chain, R3, R2, or SU2 and SU1, or U2, U1. Okay, so that's what we start with. Then this operator, as I said, destroys a downspin, creates an upspin to raise angular momentum by exactly 1/10. So that's what it's doing there, and this one does the opposite. So there's your 1, 2, and 2, 1 operators doing their job. All right. Now we're going to make them do the job for all possibilities. There's the boson oscillator state. There's the total quanta. There's the operator that's going to make it out of the vacuum. Now we're using 0, 0, just one single 0. Okay. Number of bosons for the spin up dimension, or whatever the first dimension is. It could be a B or a C, Y, Z, X. They're all possible, or any combination of them is absolutely going to give you the same form for the creation of the eigenstates. And there's the normalization that we worked so hard at doing the binomial stuff. Okay? Well, this is what it's going to be for angular momentum. Because N1 is J plus M, and N2 is J minus M. Now remember, and that should be written here, yes, J, which is nu over 2, is the nu sum divided by 2. So M comes out to be N minus 2, okay? That is, these are the relationships J and M in terms of boson quanta. Here are the boson quanta in terms of that half sum and half difference, but here's a half sum. There's just the sum and difference there. So that's the number right there that was N1, and then 2 is this number right here, and then of course I'm replacing the N's here with the J's and M's. So this has got, it's going to involve some algebra of 2 things. This one's just an algebra of 1 thing, which makes it a little simpler. And once again, that's our notation for angular momentum. The quantum number of the full U2, or R3, and then the quantum number for U1, or R2. Okay, see if there's anything else I need to say. I think that's it. Except here I'm using spin up and spin. I don't know why I forgot to put the spin down in there for 2, but I'll fix that. That's a little typo, but it isn't a significant one. And here are the relations that we started out with the review section with. These are the oscillator A dagger A relations. And here are the S plus matrices. You just replace N1 by J plus M and N2 by J minus M. Bingo. This is pages of crap in all the quantum books. It's instant here. We've got it. These are easy to remember. That's always a pain. I never remembered those things. I always have to go back to this and get that if I'm, without some place to look it up. So here's S plus acting on JM and giving me JM plus 1. If it can. If it can't, because this thing, it goes to 0, then so be it. But we have the same situation over here. We can't go outside of our N plus 1, which is the J here, divided by 2. Okay, N plus 1 divided by 2 is our J. Okay? And M is the sum over 2. Okay. M is the difference over 2, I'm sorry. All right. So, half difference number operators. There's the, where that comes in, right there. That's the M. See, it's just from this. So, that's the end of the Lie algebra as far as just the single operators acting, the angular momentum operators, or else pairs of creation destruction operators. But there's more to it than that, obviously. But let's look again. Here's the vector S plus. We've derived these things already before. Okay, actually, we did it for spin and a half, but here it is for angular momentum 1. Okay, it's Sx plus I times Sy comes out to be that. It's a raising operator. It has zeros down here and has stuff up there. It's conjugate. Take the conjugate of this thing. These are Hermitian operators, so you just put a minus sign on the I right here, and that brings you square root 2 down here, and your 0 goes there. There's the diagonalized one. The z component is diagonal. Here's the 3/2 spinner. It's got square root of 3, square root of 4, square root of 3, and then 0 on the super diagonal there. Then 3/2, 1/2, minus 1/2, minus 3/2. There's the 2 tensor, 5 by 5. We didn't have it before, but here's what it's going to look like. That's this raising operator. Lowering operator is the flip of that. Hermitian conjugate, actually. And then z is 2, 1, 0, minus 1, minus 2. That's the d orbitals have m values of 2, 1, 0, minus 1, and minus 2 possible. Making sense? It's so beautifully simple compared to the usual description of this. Really beautifully simple. All coming down from Feynman's mnemonic. Use whatever's largest in your quanta for each dimension. And then make sure you get the half sum and half difference right. Okay. Now, computation relations, that's what they use to derive all this stuff. That's really hard. Let's go back and remember our commutation relations for sigmas. Okay? It's really complicated multiplicative structure here. Okay? Sigma A times sigma B. Okay? If A, alpha, and beta are equal, it gives me 1. If they're not, this is 0. But then I can say, all right, it's one of the other sigma. And it depends on whichever index is not equal to alpha and beta. But we're already unequal. If you only got 3 dimensions, there are not very many choices. Just one choice. And there it is. Okay. So that's pretty nice, except that we want to work with spin operators, which are 1/2 of the sigmas. So the commutator formula for that one, that is this thing minus that thing, and turning that thing around turns that around. These are already 0 because they're not equal. Okay, that gives me a 2 right there if I do this. But when I subtract, that is, put the 1/2 in there, I just get this thing with no 2. If I'd done this with sigmas, I would have gotten a 2 here. For these, I get a 1. Okay, so it looks like a simple thing. That is, here's our product relation. It implies this commutator for the spin operators. That's the thing they start with in the usual angular momentum description. But there's a key Lie theorem that's always present in every one of these raising and lowering operators. All of the big Lie groups make use of what we're doing right here now, the Eigen commutation relations. These operators, the x plus I, y operators, have a very nice commutation relation with respect to the z. Now we have to prove that, but that's the result. It's an Eigen commutation relation. I apply the commutator to the S plus operator, and I get the S plus operator back with no change except for its coefficient. In this case, no change at all because the coefficient is 1. But with minus, I get back minus 1 times the operator that got acted on by z. So this is something that's really key to any Lie group, but basically it's something. Now the proof, I'm going to use the elementary matrix multiplication, the stuff that we take as pretty old stuff in this group theory course. remember the P operators, P, J, K, P, M, N, the simple matrix algebra that makes the algebra of groups so nice. Well, here our S plus is E1, 2, just a matrix with a 1 up here, and its flip, S minus, has got the 1 downstairs in the lower left-hand corner of the matrix, okay? So what we're going to do here is we're going to say, okay, I'm going to do ESZ is E1, 1 minus E2, 2. That's the 1/2 and minus 1/2. That's our spin operator with the 1/2 on there, okay? And then I'm going to do this commutation relation, you see. And the way you see that is to just go ahead and do the elementary multiplications. J, K, M, N is 0 unless K is equal to M, and then it's equal to J and N, the outside indices. Just go through and do all those multiplications, remembering this is a commutator because you got to multiply and then you got to multiply the thing with a E1, 2 on the left-hand side. You will get this and you will get that. It's easier just to use these matrices and show that it's true. That's the quickest way. Either way, QED in the finest script you can find. So this is a very easy to show relation for our Lie group, which only has 3 generators. For other Lie groups, then they go on forever. You can have any number of generators, but you'll still have this theorem to work with, slightly changed. Now here's one that's rather remarkable. This one is going to go through and give me a product of E2, 1, 2 times E2, 1. Well, that comes out to be E1, 1. Then I'm going to flip them around, and I'm going to get E2, 2 now, because the 1s are going to be facing each other in the product. Well, that's 2 times SC. So that's another operation, another commutation relation that the people that do this the ordinary way have to know. So there's a general Eigen commutation theorem that should be stated for later work in bigger Lie groups, and that is that the Hamiltonian, if you have a Hamiltonian commuting with a creation operator, you'll just get the creation operator back again. Same with the destruction operator. And this one's formation, there's no plus or minus sign to worry about here. But if you have this, then the thing has to be a combination of that. Vice versa, if it is a combination of that, then you do have this. So you really have no choice there. So this is the thing that I point out to you, is that our original harmonic oscillator formula for a Hamiltonian has a representation in the fundamental basis of omega 1 and omega 2, the frequencies of the 2 dimensions. Very trivial, you know, for the oscillator world. Rather esoteric, you see, in the angular momentum algebra world. So there's the U2 oscillator eigensolutions right there. It's just frequency, fundamental frequency, times number of quanta. That's one dimension. Second dimension. Again, second dimension frequency times the number of quanta in that dimension. That can be written for angular momentum like this. J plus m and J minus m. You see, it's just a little bit more complicated for the angular momentum. Now we're going to do the full thing here, because what I want to do is look at the square of this operator. The sum of the squares. Okay? Now that turns out it's S plus S minus plus S minus S plus and Z squared. You can see that from the elementary operator description. Now, let's do it first, the fundamentals. Okay? We know what the answer is. Each of these things is a half sigma. Sigma squared to 1, right? This is going to square to 1. 1 unit matrix. This is going to square to 1 unit matrix. So we're going to get 3 unit matrix times a half square, which is a quarter. So you get 3/4 for your total angular momentum squared. 1/2 squared is not 1/4, it's 3/4. That's a lot more than 1/4. Let's keep this going. Okay? We're going to do it for general now. So what we're going to do is we're going to write out S plus S minus, S plus S minus, S minus S plus, S minus, S plus is just a commutator, commuted of this, okay? Then number operator, that's not so bad, just number operators. This is not a bad thing. I know this in terms of N1s and N2s or J's and M's. This has got to be unraveled. This is where you got to put the those darn destruction operators, those horrible Republicans, off on the right. And the nice left guys can go on the left. So we're going to put all these up. We're going to get it ordered so it's like this. That means I have to reorder this one, and I have to reorder that pair right there, and I'm done. Then I'll have it in normal form. Okay, normal order is creation operators on the left, destruction operators on the right. Okay? We use this relation here. So I rewrite that 1 as A22 plus 1, and then A11. So I bring this A2 inside this. Let's see, that's an A11 plus 1 there. And then these I leave alone. Okay, now it's in a form where I read it all. It's all number operators. Okay, I'm going to get an N2 plus 1 here times an N. Okay, go factor 2. Same thing here. N1 plus 1 times N2. Then this thing is just N1 minus N2 twice. So there's your eigenvalue for S squared. Now we've got to make sure that we get 3/4 for the general, the elementary case, the fundamental case, but that is a good thing. Now this is one case where the answer in angular momentum quanta, J and M, is simpler than this. Take this, and this, and this, and this 4m squared, there's a thing that's going to be multiplied by 1/4, you get this. J times J plus 1. That's really cool. Now once again, all of this, really this is the main line right here, this step. It's much more complicated to do this just using the S operators themselves and their commutation relation. So and this is interesting, for large J, the magnitude of an angular momentum approaches J plus 1/2. Okay, what I'm talking about is the magnitude of S squared. Okay, that's the square root of S squared. Okay, positive square root. That's this J plus 1 square rooted. Binomial theorem gives this very nearly, it gets there pretty quickly as you go up in J plus 1/2. We're going to make use of that. That's an absolutely powerful piece of angular momentum lore right there. We're going to use that to evaluate a number of different things. The first of which is the angular momentum uncertainty angle. So this is a way to take these very precise quantum mechanical eigenvalues. First of all, the z component is m. So I mark off a z-axis with j equal to m minus 1, and m equal to j minus 1 is the next one down. This one right here would come across for this thing. And the idea is that this is a geometry of it. You see, because this thing right here is square root of j times j plus 1. Okay, very nearly equal to j plus 1/2. Very similar to what we had with the first quantum oscillator. We have 0, but then we have the 0-point motion as 1/2. Then we go in integer steps after that. That's basically what we have here. You jump 1/2 from j to here, and then from there on it's integer steps. Here's an example, j equal 30. There's an angle for each of these cones. Because this magnitude here is 1/2 bigger, right? The vector doesn't just sit on the axis. The vector has to get pushed out, and the further down we go, the more the uncertainty the uncertainty of the x and the y components go. Z is perfect. We really know what the value of z component is. It's an integer, m, times h bar. I'm leaving all that out. Okay, the units out. The angular momentum is action. So it's so many joule seconds. We're talking about it in units of 10 to the minus 34, roughly. Here, h bar. But these angles are really crucial for stuff we'll be doing later. Really good to know that. Very simple. Arc cosine of the whatever level you're at. That's the usual molecular notation for m, the height of these base here, okay, divided by the square root of j times j plus 1, divided by j plus a half, square root. I'm sorry, not without the square root. Okay? All right. Now, we do have a little bit of algebra to do here now, because what I'd like to do is find out what the higher than fundamental representations, that is the 3x3, the 4x4, 5x5 in particular, we're going to look very closely at that one, the d orbitals, but also the p orbitals, or the 3x3s, are of interest here. Now, all we've got so far is an Euler representation of the 2x2, the fundamental representation of the 2.
Sorry, in the last page.
Last page.
Is that really real, considering this direction for the spin? I mean, is it correct?
I guess a better way to say what's going on here is we're honoring the tradition of the fundamental religion of Arkansas. And that is to take a literal interpretation of the text, right? And deviate not from that, right? Here it makes sense to do that. There it doesn't. But the idea is that if I have, this is my z component, okay, this altitude right here, and if j was just equal to, you know, what its usual thing, we would start right on the axis with no uncertainty at all. And then we'd have a different value. But we have to be strict to the rule here. I have to make sure that this is this.
Is it j2?
J times j plus 1 square root. J squared plus j square root, which is j plus a half. So if I do that, then each of these is a triangle with a hypotenuse equal to that, and a base equal to the m, right? That puts you at this angle that we're talking about here, arc cosine, and these are the values for it.
No, but in reality, in experiment, I think considering the direction for spin,
we're going to do that. We're going to do
we just have two directions for spin, up and down.
Well, that's the z component. Now we're trying to track the other components.
I mean, it is impossible for us to measure angle for spin.
Yes.
When we change, but just we can have plus and minus.
Not in the way you'd think, but yes, we're going to. You see a little bit of it going on right there. That's what we're going to do. We're going to try to do that. Okay. In other words, we're going to tell the whole story of angular momentum now, not just the z.
Yeah.
Okay. And it's beautiful. It's really gorgeous.
Yes, it's beautiful.
It's really nice. We'll do it for j equal 20, which is not too different from this, but the angles are all very different. They're just the same idea. Okay, now as I said, what I'd like to do is generate all of the others using creation operators, you know, the powers of them, right? But I'd like to do it, for any operator, any direction, any alpha, beta, gamma. I'd like to do that. you see. And we already have this as our SU2 matrix, right? This is something we derived before, right? This is a fancy way to write it, right? I put the gammas, you see, that would normally be, remember we just looked at that much of it, and then the gamma sat outside as an overall phase, minus gamma over 2. This is the whole story here, okay? So these are the irreducible coefficients, each component matching each of these. Or this is the nicer notation perhaps, where 1 and 2 means spin up a half, or down a half. That's down a half right there. Okay? But here's the transformation between spin up and down that are straight up, and spin up and down that are over and twisted, you see, and, you know, turned by angle alpha, beta, gamma. That's really what we've got here. Now we have to do that for spin more than a half. 1, 3 halves, 2, 3, 4, so on. 20. Okay, we've got to do that. Okay, and that's what we're going to do. Simply by taking linear combinations of our old creation operators and making new ones that are those combinations right there, that matrix combination right there. Okay? So this relation needs to be generalized. Okay? So here's what we're going to produce. We're going to produce the effect of a rotation operator to alpha, beta, gamma on any angular momentum state. And any angular momentum state Jn is given by creation operators to j plus n and j minus n divided by square root of j plus n, j minus n factorial respectively on the vacuum. So we're going to have a binomial algebra problem here. This one right here has got to be the creation operator A1 prime, the one that takes you to alpha, beta, gamma, 4 spin up. Then spin down prime has got to be here with the power j minus n. So that's the algebra that you've got to do in order to get the representation of this rotation operator for arbitrary Euler angles and any angular momentum and its component. So that's a big order, but that's going to do it. That's what we're after. Well, we've got to do some binomial expansions using coefficients that are binomial. Okay. So when I put in those binomial coefficients and then do a sum over L and K, I get what looks like it's going to be a mess. I get, you know, 1 power here, and then I get that j plus n minus that power. And k here, and I get j minus, and again, minus k there. Okay, so I'm being summing over this L and the k. I obviously have to sum over different combinations of those integers, because we want to we want the final answer to be in the j plus and minus m form. So I just declare that this particular L plus k here is j plus m. And this 2j minus L minus k right here, I want to call it j minus m. Okay? Then, if I resort those coefficients in that thing, I should be getting that form, j plus m, j minus m. Then I just have to look for the square root of j plus n and j minus n in there and pull out my irreducible representation that I'm looking for. That's the general result. This is blown up so you can see it, what you get. I get a matrix element, that's the djmn, that has this is the j plus and minus m for the one side, and this is j plus and minus n for the other side. Then I get here these things, putting it back in a notation. I can go ahead and you put a cosine in for that one, a sine in for that one, and then these things are just exponentials, phases. So there it is. That's the irreducible representation for SU2 and R3, but once you got SU2, you've got R3 in the bag as well. All possible group elements, all possible J values, and sub-J, sub-angular minimum values. This is an amazing result. Really cool. Now we've got to look at it. It's got all those cones and things hiding in it. Okay? So let's look at some of the applications. The first one, just to get you familiar with what it is that it's given us. Remember that the alpha, beta, and gamma was a Z rotation by gamma first, beta second, so that's the one that's got the meat in it, and then alpha afterwards. So this is the phase stuff, and this is in the body frame. This is the phase stuff in the laboratory. Okay? We're thinking about this thing in that terminology already. If I put those two together, I get this thing. Okay? Now, everything is in half angles because that's what spinners use. But we can easily turn the beta over 2 into a single beta instead of a half beta. 1 plus cosine beta, which is cosine squared of beta, which is sine squared. See, they're all squared in the relationships that you get from the formula we just derived. And then the products, too, also turn into single angle. So that has been used here in this formulation. Okay? And the thing that's really neat about this is it's not just a transformation matrix that you might use not so often, although we're going to use it a lot today. The thing that I would like to show you right away is the center column. That is, with a factor, 2L plus 1 over 4 pi, is exactly, with every phase and normalization in place, the spherical harmonics, which, you know, it takes a lot of work in a quantum book to derive those things through series, right? Here we're going to be given them. You take this one, and this one, that's y1, 1, that's y1, 0, that's y1 minus 1. The only catch is you've got to conjugate this. But that we've been doing all along. When we had e to the minus ikx as our irreducible representation, right? That was a character or irreducible representation. The wave function was e to the ikx plus I, right? The conjugate of this. Same thing happening here. So I do have to take a conjugate to get back to a wave function. That's the only thing you have to do. These are the correct normalizations. You see, the group already knows how it multiplies. So it's got the normalization down. That's the hardest part of doing it by series, right? You get these funny series, and then you got to take the series and square them and try to figure out how to make them 1. It's automatic here.
So in the finite group, we had a script L over capital
That's
N
right.
factor, and this is the exact same thing. Now, instead of summing the N,
This
we
is
have
the
to
equivalent of that. That's right. Exactly. Yeah.
integrate.
The catch is that it's an integral over parameter space, and parameter space has an infinite number of elements. So it isn't just L over order of group, because that would be 0. Order of group is infinite here. So it's a measure that we're getting for essentially free. I'll get to that. That's an important question, obviously. Okay, so there's your dipole functions right there. X plus iy, z, and x minus y divided by radius are the other part of the spherical coordinates. It's a radius, and it just sits outside of all of this. Okay, so that's your wave functions right there in terms of x and y. The transformation between x and y and z and circular polarization, that's what this is. That'd be right circular, this would be left circular, there's just z polarization. Those are the 3 parts of a optical beam to the multiple order of 1. We've got a dipole here, dipole order. Okay? So this transformation is useful for turning this matrix into something you recognize. if I apply this transformation, it gets me out of the complex basis that has chirality, the C basis, and into a Z basis or an A basis in our language, you get this. That's our familiar rotation around Y. And while you're at it, you might as well do the others. The alpha one gives me this. And we've got two of those in this alpha, beta, gamma product to make that. And we'll be using that for all the others too. But that's the thing you'll have to do here. And then when you put it all together, that is, turn this matrix, this whole thing with all this complex stuff, into real stuff, we've seen this before. There's your polar coordinates in the laboratory. There's your polar coordinates in the body. Then there are all the other coordinates being mixed up by a rotation of alpha, beta, gamma.
I know this exactly. It is Euler-Angels matrix. But I don't know the first part, D, where
here.
That came.
This thing.
And how we can find this C matrix.
Well, I did it sort of sneakily right here.
Very fast.
What you would do is you'd take the Z rotation and diagonalize. This is the transformation that would diagonalize.
Oh.
That's one way.
Z rotation.
You use projections to do that to make it simple.
Mm-hmm.
But yes, that basically when I recognize in this that I have x plus iy over the square root of 2, then that's what I write.
Mm-hmm.
You see, I go reading the thing x, y, z. That's basically what it comes down. Here's just z by itself, either way, okay? And then it doesn't sound like I know what I'm doing here, but that is a way to take this relationship here. You see, this is minus x minus iy.
Yeah.
That would be this thing and this thing. And then this is x minus y, so let's see if that's right. I'd have to be careful, because there's an extra phase that this thing, this throws in here. Either this one or both of them. I think it's both of them. I do it this way and I do it this way. That lets you, just turn this relationship here. You see, it's easy to get this because we know the polar coordinates x and y, right? Once you have that, then you could make this matrix fairly quickly.
The coefficient of the y is I over 2, so
X, Y, Z.
Yeah.
1.
I think.
Ooh, let's see if I've got that right. This is 1 to X. This is 1 to Y.
Yeah.
That should be plus 1 to Z. Yeah, that's the typo right there. You're very, very right about that. This is 0 to X, 0 to Y, 0 to Z, and then minus 1 to X, minus 1 to Y, and minus 1 to Z. That's a typo for sure. That should be plus 1.
I think it is the coefficient of the y
Yeah.
goes there,
Yeah.
and the other one coefficient
Well,
of the
here's the
minus
one that
1
goes with this part right here, and then this thing right here, and so forth. The
I think the other one should be I minus I over 2, if I'm right.
that could be this one right here. You say?
The other one minus.
Oh, this one.
The at the bottom. I mean I over 2.
The way I would look at it is this is x, y, and z.
Mm-hmm.
Okay. This comes out to be minus
and
minus.
Okay.
Right?
Okay.
You see?
The minus one, yeah.
Yeah. So
It's okay.
there should be a minus there.
If
Th-
it
this
is
thing
minus
becomes C.
there, at the bottom we have to have minus. But
And this one would have to be minus. Yeah.
If it is that.
Yeah. We'll have to fix that one. It's got two things in it. But in any case, once you get it right, these relationships follow. And I'm wondering why it worked. Let's see if I did that. Well, we'll look at it later, but in any case, that's the main point. What I want to do is get on to what the wave functions look like. This is a picture of this thing. Now, that's what a cosine looks like if you plot it radially. It's a circle, but it's got azimuthal symmetry, so it's a sphere. All the other ones are the same way. They're just cosines in different axes. So that's a correct rendition of the amplitudes for these matrix elements, but also for the wave functions that come with them, or that are derived by them. So those are what we call standing P waves. This guy, and this guy. No complex numbers at all. The moving waves, they're the standing waves. The moving waves, these are the standing P wave distributions. If you square these, then it becomes egg-like. If you square the circle, if you square the radius, you see, it gets longer, you see, so they elongate.
Oh.
Okay? So these are the squares. And then the moving wave representations can be drawn. Okay? They're distributions, right? And these guys cannot, because they have angular momentum, have any probability at all to be on the z-axis. So they absolutely go to zero on that axis. So that's the moving P's. There are two of them, and one of those, that makes up your three triplet. All right, let's go to D. That's what the D representation looks like after you get done sanitizing the halves using a cosine relation and sine relation. Okay. Again, the middle column is the wave function for ordinary angular momentum quantum mechanics. What we've got is a wave function for an entire rotor. This is just a rotor that can only spin, it only produce angular momentum perpendicular to its axis, like an electron that has no spin, or a boson of some kind that has no intrinsic angular momentum. You only have orbital angular momentum. These are the 5 states you're limited to. Okay, what are they? Well, the real parts of this, and that one's already real, so that's pretty easy. That's this one right here. Z squared minus x squared minus y squared is what that is. Okay, actually it's 2z squared minus x squared minus y squared. See, this is x squared plus y squared plus z squared. With a minus sign, that brings this z squared down to 2, leaving x squared and y squared each with a single minus sign. So that's this function right here. That's a Legendre polynomial P2. These are associated Legendre polynomials y2, 2, 1, 0, minus 1, minus 2. Okay? Or multiple functions if you multiply by the radius to the kth power. Rk, yk is the same as xk. Those are called multiple tensors or x functions. So we're getting all of that for free by just looking at the middle of this thing. But most of the physics is out here. The really interesting physics is out there. But you can see these are very important functions going on in the basement of this building. Directly under us is Jock's lab, and all he worries about is how the D functions go with each other in a crystal. And that makes all these new devices that they're coming up with. So it's really a lot of physics just in this center column. But we're going to go outside of that today, because that's what we do on the second floor. We worry about molecules. And they have a body, and there's body components. There's a Mach-Mach principle that has to be respected here. Before we do that, let's go over what the Mach-Mach principle would be. in the basic thing here is we have a sum over all the elements of the group. We have to do an L over, well, order of the group, but it's not going to be order of the group. It's going to be the size of the integral of the differential, alpha, beta, and gamma. That is d alpha, d beta sine beta, and d gamma. This is the body part of it, and this is the connection between body and lab, and then this is the lab part. Now for R3, this comes out to be just 8 pi squared, because I only integrate between 0 and pi. That's all I have to do. I don't have to go from minus pi to plus pi, but I do have to take the other angles over 2 pi. Over for SU2, or U2, okay, for half integral, the integral must go from minus pi to pi. It's twice as big. This group is twice as big as this one. So that's the difference. So you get 16 pi squared as your normalization for that. Other than that, the formulas are very simple. So the eigenstates of angular momentum are built from projection operators just the way we did. It's just we have to be careful about our sum. Our sum is an integral now. So here is the group projected state Jmn. Now both quantum numbers are needed, not just the m, but the n for a full molecule is going to be important. So I do an integral over the Euler angles, which is the coordinates of a rotor like this machine is trying to symbolize that we were using for discussing Eulers and Darboux and all that. Okay, but anyway, it's going to be a sum with a normalization here and an extra dimension, square root, multiplying that there. That's your wave function, right there, apart from these two factors. Once again, the irreducible representation transforms the wave functions, but it also is the wave function. And that's something that really has to be recognized, and of course, that comes with the Mach-Mach principle that we talked about. As far as Euler angle 0 goes, which is the singularity for this thing, a laboratory transformation of that will give me a state that has the same relative position as going inside and using their transformation, which commutes with this one. Okay, moves the whole universe, leaves the body alone, right? That sounds crazy. That's what I call Mach-Mach, but that's what we're using here. They commute, they are connected with the original state. That's what gives all of the states that we're going to be talking about here. All the rotational states are going to be combined to make a wave function. This is the wave function that will be there. But the effect of the operator is this. This one will sum over m's. This one will sum over n's. That's the difference. Not only that, it uses starred wave functions. It's a conjugate to this one, but it's the same function otherwise. Okay? And the same applies to the generators. The trouble with this one is it gives a minus m. That's the little detail that we're going to zoom by right here, but it's because it is a conjugation. It's turning the other way. Okay, now let's look at this. This reversed sign is a nuisance. So what I do is I take the little bar off the z that represents the body component and stick it over the s there and have a minus sign. That's my definition of sz bar. We're going to take the viewpoint of the laboratory and we're going to use that as our operator. So when we talk about a symmetric top molecule, it has inertia 1/2 times the angular inertia on the x-axis. It's equal to the one on the y-axis. That's what makes it called a symmetric top. And then a different value on the z-axis. This would be the Hamiltonian if it was rigid. Rigid rotor. Okay? The constants are the inertia, and we're going to demand y and x body frame coordinates have equal values. Then the z component will be something else again. Now, the Hamiltonian can be written in terms of two commuting observables, z and the square. Okay? You start out with this, then basically you add and subtract b times j z squared. Z bar squared, these are all barred. Okay? So if I do that, if I get this sum right here, that's just j squared, and we know the quantum number for that square, the value of that is j times j plus 1. And this one has got whatever the quantum number we're going to name for the body quantum number. N is what we're using here, N for nuclei, or nuclear frame. Okay? So the eigensolution equations look like that, and there are the eigenvalues. A prolate, sort of bowling pin-like molecules, CO2, if it was bent, water is asymmetric, so I'm not going to use that, but say C3 or any of the molecules, if they were rigid, okay, would have a spectrum like this. Now you see what's amazing about this spectrum is that you're talking about a bigger multiplicity than we're used to. The multiplicity for each angular momentum j here is 2j plus 1 squared. Each one of these quantum numbers gets to its day in court, so to speak. But because it's an internal symmetry breaking, it's the n's that split out, not the m. The m is still hiding at every one of those levels, and there are 2j plus 1 of them. There's 3 of them down here, besides the 3 n's, which gives me what looks like just 3 different levels, 2 of which are degenerate. But every one of those levels is 2j plus 1 degenerate. So there are 9 levels here, and 25 here, you see. Okay? Now, here we're talking about 7 squared, 49 levels hiding in there. Each one of these is 7-fold degenerate. That makes 14 degeneracy there, 14 degeneracy there, 14 degeneracy there. Now this is a flat molecule, this is a elongated one. Up and down they're going to go, it depends on the sign of A minus B. And this is the best way I can picture what we have here. This is the idea of an angular momentum J that has a cone in the laboratory frame and one in the body frame. And they're going to be going around with a J here and various things processing or doing whatever they're allowed to do in what we would call the fundamentalist model of the quantum angular momentum cones. But the cones are going to have a definite geometry, depending on what quantum numbers I pick for m and n. And I have quite a choice here. For just j equal 1, I've got 9 possibilities. J equal 2, I got 25. So it's huge in terms of the structure that's waiting here to be understood. So as I say, the n equals 0 levels, they're easy. They're non-degenerate as far as the body's concerned, but the laboratory says, no, I've got my degeneracy too. So the n equals 0 is 2j plus 1 degenerate. The others are all 4j plus 2 degenerate. Now we have to try to get some pictures of this, and this is what's really cool. Later on we'll talk about the tensorial Hamiltonians. That's the generalization of spinors that we still have to do yet. But when we do that, the quadrupoles are very interesting, and this particular Hamiltonian is made of a very simple quadrupole plus a scalar. Well, the eigenvalues of that are exactly what you get if you put the angular momentum cones here and then demand, you see, that each one of them matches with its particular angle. So the actual spectrum, if you plot energy radially, is indicated by this curve right here. It's just gotten from that formula and the tensor Hamiltonian, which starts with a thing we just wrote down. So that's something else we have to look at, but that's where the where these cones become quantitative and really very useful. Now, one last thing, if we have time here, and it's pushing it. One last thing is I want to do the general Stern-Gerlach. Remember we started this course with spin a half going through magnet, right? Or a polarization, really was spin 1, but it acted like spin a half because there was no intermediate component. Okay? Well, now we're going to do it with angular momentum 2. So I'm going to have 5 windows in the analyzer. So here comes a beam of spin 2 particles, d waves, with their little angular momentum cones in various positions. And I'm looking at what happens if I rotate the 2-1 state, for example. If I rotate the 2-1 state, what happens? Okay? Well, it gets rotated, but then if it has to go back through the original kind of analyzer that's aligned perfectly with the vertical, then each of these possible outcomes is possible from just this one. And if it's just a little angle, this would be pretty much the whole story. And if it was 0, then it would be the whole story. Nothing would come out here, nothing would come out here, nothing would come out here, nothing would come out there. So these things had better be 0. This one's 0, this one's 0, this one's 0, this one's 0, this one 1 for beta equals 0. Okay? So this is a way to look at the transformation by this rotation operator of a particular angular momentum state. And this is useful for atomic physics as well as molecular physics. So this is the kind of angular momentum theory that atomic physicists know. They don't know about this thing as a wave function. They just know it as a transformation coefficient. And so here is the overlap state with the unrotated states. Okay? So as you can see, at beta equals 0, nothing here, nothing here, nothing here, and nothing there, but 100% right there. Now one of these is d squared, that's the red one, okay? Absolute magnitude squared, so if there's any phases or anything in this thing, they'll be out of here. And then this thing right here is the actual value of the d function, and it's real because it's a y rotation only that we're doing. And so I'm putting the real value in blue here, and then the square of it is in red. Okay? Now if I turn the thing completely over, the analyzer completely over, okay, then it would be the -2 that would come out, the thing, -1 that would come out if I did that one. And you can see there's a 1 there, but 0 and 0 and 0 and 0 there. So this is a generalization of the polarization experiment of Stern and Gerlach that started the whole quantum angular momentum business. But now we can do this for any J fairly easily. And here's a picture of the whole matrix of possibilities. We were just looking at the J M1 row here. Now let me get myself squared here. This is -2, -2. This is -2, -1. So what we're seeing in that column right there is very similar to what we were looking at, but actually what we were looking at was this one right here, which comes out let's see if that's right. Here's the one that we're looking at. It's going the other way. There's 1 and 0 for everything else. Okay, for that one. And that's true for the whole, anything on a diagonal here, you see it at angle 0. You always have 1. In any case, what we want to do is look at what really is going on in that. And that's the next story here. This is a modern picture using this particular app, which you can work at your leisure to study these things. But here is another way to look at it that's really cool. This is plotting the thing versus M prime. That's the first index, the laboratory index, for fixed values, okay, of J, beta, and M unprime right here. So we're going to be plotting versus the quantum number for a fixed angle, okay, and here's what you get. And this is where the angular momentum cones really show where things should be. Because if you think of the angular momentum coordinate in a literal interpretation, then it would be a J vector constrained to be at that place where it has the right Z component and the right length, which causes it to have a radius of, and that on a cone. There would be whizzing around in a phase space here, back and forth on that. If you project this down, it goes right through the inflection points of this set of dots. If you can imagine a curve going through them, and we don't have that curve. We just have the dots. Our function, our d functions are functions of those integers. Making them something else that doesn't make sense. But this cone does make sense. Now I'm going to switch over to this one so you can see this for angular momentum 20, just to get a feeling for what it's doing. And what I'm going to do is start out here with J20, N20, and I'll make the angle smaller now. That's almost 90 degrees that you were looking at there. As I bring this thing down, you see, and I've got 20 times 2 is 40, plus one state there, one state being the 0 state. Plus and minus 20, and then the 0, that's 2J plus 1, 3 times 20 plus 1. As I approach an angle that's small, look what's happening. This curve that we see for those blue and red dots is having some problems. Because eventually, as I make this thing at 0 angle, and I have to get over